Welcome to the second part of lecture 2, where we are discussing different examples to illustrate how to compute power consumption using 3 laws of comminution. Now in this part we will consider third example. Example 1 and example 2 we have already covered in part 1 of this lecture. Now example 3 goes as: sphelerite having density of 4000 kg per hour is fed to a crusher at 10,000 kg per hour in closed circuit. Now if you consider this diagram, 10,000 is a feed to closed circuit. So when we consider the closed circuit, obviously capital F would be the feed, which we have considered as 10,000 kg per hour. Crushed material passes through the screen of 0.417 mm size. So this screen size is 0.417 mm. Rittinger's number for the material being crushed is 0.0573 meter square per joule, and the crusher consumes 3 kilowatt when running empty and 5 kilowatt when crushing the sphelerite. So that is the consumption of crusher. Now what we have to compute is the overall as well as theoretical efficiency of crusher. Therefore, for this problem the associated data for particle size distribution is known to us. Here we have the capital F is basically the makeup to the crusher, its distribution is given. Discharge from the crusher, that is the PC value, it is given, and oversize from screen, that is the R value. So fractions of R are also given over here. So in this particular problem, number of screens we are considering where the size vary from 6.68 mm to 0.074 mm. For this problem we have to calculate overall as well as theoretical efficiency of the crusher. To calculate this, first of all we should understand, we should calculate the power consumption for crushing the feed. So this is the data for present problem. As in the present problem Rittinger's number is given, so Rittinger's law is applicable in this example to calculate power consumption. So to apply Rittinger's law, specific surfaces of feed as well as final product are to be computed. Now for feed we have selected F stream and for final product we have selected PF stream. Now why I have selected F as well as PF? Because we have to calculate power consumption for closed cycle. So F is the feed to closed cycle and PF is the product from the closed cycle. So when we apply the Rittinger's law, the expression goes as E by M equal to SP minus SF divided by Rittinger's number. Rittinger's number is already given to us, SP and SF we have to calculate. So SP and SF we can calculate using these expressions. So before starting the computation of this, we have to draw all data from this given particle size distribution data. So to find fraction of capital F as well as PF, mass balance is applied around 0.417 mm screen. Because F is given to us and fraction of F are already known to us, we have to calculate fraction of PF. So we will make the balance over here where PC is equal to PF plus R. So PC is equal to R plus PF. When we make the component balance, PC into XPC equal to RXR plus PF x PF. We have to calculate XPF for different fractions. Further we can rewrite the expression as PC divided by PF, that is the ratio of PC over PF into XPC equal to R divided by PF into XR plus XPF. Further this R divided by PF we can replace using this expression where R over PF can be replaced with PC over PF minus 1. So if you see this particular expression we are getting in terms of ratio of PC over PF. So, finally, we have PC over PF into XPC equal to PC over PF minus 1 XR plus XPF. We have to calculate XPF from this expression. To calculate XPF, at least we should know all these data. However, if you see the data which are given to us, only F is given to us, not PC or PF. If we make the balance around closed cycle, then F would be equal to PF, but along with PF we should know the value of PC also. So, how we can calculate the ratio of PC over PF? For this we have used the analysis which goes as, if this screen is having size 0.417 mm and I want to calculate the particle size distribution of this, then I can assume that the material which is available above to this would be 0, because if I am considering undersize, it means I can assume that particle which are available above to these screens would be 0. For example, here if you see this table, here on 417 this much fraction are retained. So, if I consider this screen, it means above to this all XPF value would be 0. Considering this factor, for example, if I consider this particular interval, so here we have PC value or XPC value is 0.06 and XR value 0.09. So, these value we can use to calculate the ratio of PC over PF. So, PC over PF into 0.06 is equal to PC over PF minus 1 into 0.09, and here we have considered XPF as 0. Now, resolving it, we can have the ratio of PC over PF as 3. This ratio we can put in this particular expression, and finally we have XPF equal to 3XPC minus 2XR. Considering this equation, we can calculate fraction corresponding to PF stream. Now, here you see for this particular section where the size shows as minus 0.417 plus 0.296, because above this we have assumed all value of XPF as 0. So, XPF expression I am having in this form. Considering value of XPC and XR as 0.32 and 0.34, I can calculate value of XPF which is 0.28. So, 0.28 will lie over here, and in the similar line following the same expression we can calculate value in other fractions also. So, this is the complete fraction of XPF. Now, once I know the XPF, to calculate specific surface of feed and product, we have to calculate D average, because this D average is required in SP expression as well as SF expression. How I can compute that D average? By simply doing the arithmetic mean of these two value, and we can calculate D average. For example, in first case, in first interval, the D average would be equal to 6.68 plus 4.699 divided by 2. So, value comes as 0.00569 meter. Following same expression, arithmetic mean of these two value which are given over here, we can calculate D average of each interval. So, all D average I for SP as well as SF are known to us. Once I know the D average, next value of N we have to calculate. Once I know D average, the value of N should be calculated next to it. How I can calculate value of Ni? The Ni is basically specific surface ratio for ith interval. So, for each interval I can calculate this. How I can calculate this? Using the value of D average as well as this particular graph. This graph, I guess you remember this, this we have discussed when we were discussing the specific surface ratio. In this particular problem, the feed is sphalerite, and here corresponding to each D average value we can calculate, we can see the value of n from this graph. For example, initially I am having 5690 micrometer somewhere here the value will lie, and curve 3 we will use to see the value of n for sphalerite. So, once I draw the line corresponding to 5690 and corresponding to 3, I can see the value from this axis which comes out as 5, and in similar line I can calculate, I can see value of n for other intervals also. So, here you see we already know D average I and Ni for computation of SP as well as SF. Now, I have to calculate the specific surfaces. These are the expression for SP as well as SF. So, first of all we have to calculate N1 into XPF1 divided by D average 1 for first interval. So, here you see the value n is given to us, though XPF1 is 0. So, whole expression becomes 0. So, here we can calculate the value of NXPF1 divided by D average 1 for first interval, and similarly for other intervals also. In the similar line we can calculate this for feed for each interval. In this slide we have shown different value of NIXFI by D average I, and its summation is equal to 1609.917, and similarly NIXPFI by D average I, its summation is equal to 9462.913. Considering these two value, we can calculate SP minus SF, and when we see the expression of SP and SF, in this expression 6 by rho is common. So, SP minus SF we can calculate as 6 by 4000, which is the density of sphalerite, and value of summation is given as 9462.91 minus 1609.92. So, after resolving it, SP minus SF we can find as 11.7795 meter square per kg. So, basically SP minus SF is nothing but the new surface created, which we have used in Rittinger's expression. Using the value of SP minus SF as well as Rittinger number, we can calculate E by m value, which is the energy consumption per unit mass. So, here you see value which is coming to us is 205.5758 joule per kg. When we multiply this with the feed, which is 10,000 kg per hour, and here we are given joule, so we have to convert that in kg per second. So, once I do this and multiply with 205.5758, the energy consumption comes at 571.05 watt. This is the energy consumption for new surface created. Our aim is to calculate the efficiency for overall crushing as well as theoretical efficiency. So, how I can compute this? Considering the initial energy consumption given to us, and these are crusher consumes 3 kilowatt when running empty and 5 kilowatt when crushing the sphalerite. So, you see the value of total 5 kilowatt is the total consumption of energy, and 5 minus 3, that is 2 kilowatt is used for creating of new surface. So, overall efficiency would be 11.4. How we can compute this? That 571.04 divided by 5000 into 100. And similarly, theoretical efficiency we have calculated as 571.04 divided by 2000 into 100. So, that comes as 28.6%. So, in this example we have used the Rittinger's number and specific surface of feed as well as product. So, that is all for example 3. Now, I am having example 4. In this example, a grinder with 10% efficiency is used to crush 7 ton per hour of coal. The feed consists of 20% by mass with diameter of 10 mm, 50% by mass with diameter of 8 mm and balance having the diameter of 5 mm. However, the screen analysis of the product is given in this table. What we have to compute is actual power consumption of the grinder using Bond's law. So, here you see the efficiency of grinding is given to us, we have to calculate actual power consumption. So, as far as data is concerned, we can tabulate the data like mass fraction of feed and product. If you see the feed having 20% of 10 mm size, 50 mm of 8 mm size and rest 30 mm of 5 mm size, and this is the distribution for product. We have to use the data given over here for feed as well as product to compute the energy consumption using Bond's law. When we apply the Bond's law, this is the expression for Bond's law, we have to compute dPb as well as dFb. dFb is the size correspond to 80% in feed. So, accordingly dPb would be the size corresponding to 80% in product. So, if we see the mass fraction of feed over here, that is 2, 0.5 and 3, first of all we have to make the cumulative of this. So, corresponding to 80% the value of diameter or aperture is given as 8 mm. So, that we can use directly over here. However, for product these are the fractions we are given. First of all we have to make the cumulative of it, and you understand when we make the cumulative from bottom we use all minus signs of the aperture. So, in this product analysis we will lie somewhere here as far as 80% is concerned. Therefore, the dPb value will lie between 4 and 2. If we make the interpolation in between these two, we can get dPb value as 2.462 mm. Further, the feed as coal is given to us and we have been asked to calculate using Bond's law. So, work index is required for this purpose. We can refer this table where work index corresponding to coal is given as 13 kilowatt hour per ton. So, using work index value dFb and dPb value, we can calculate the power consumption using Bond's law, and which comes out as E by m equal to 1.166 kilowatt hour per ton. Total feed which is entering to the crusher is 7, so that we can multiply with this. So, capital E, that is power consumption, is coming out as 1.166 into 7, which gives the value 8.165 kilowatt. For this particular problem, the crusher is having 10% efficiency. So, actual energy consumption would be 8.165 divided by 0.1. So, 81.651 kilowatt is the energy consumption for this particular example. So, in this slide we have considered fifth example, and this example goes as feed of 120 tons per day of quartz is comminuted in a grinder which utilizes 50 kilowatt of energy. The particle size distribution of feed as well as product are shown here. A ball mill is used for this purpose which has 30% theoretical efficiency. So, total energy consumption of 50 kilowatt is given to us and theoretical efficiency of 30 kilowatt is known for ball mill. What we have to calculate is the energy consumption in the mill when it runs empty. So, to calculate this, again we have to calculate the power consumption for crushing the material, and using expression of theoretical efficiency we can calculate the energy consumption while running the mill empty. So, in this problem we have to use Bond's law. So, the data which are given to us, that is for feed distribution as well as product distribution, and here if you see the first column of this, here we are given mesh number of Taylor screens, and here mesh number are given to us, not the opening of aperture. So, let us start solving this problem. To use Bond's law, work index of quads is required. From this table we can see the value of work index of quads, that is 13.57 kilowatt hour per ton, and this is the expression of Bond's law, where we have to compute diameter, where 80% product is passed through the screen, and here we have to calculate diameter where 80% of feed is passed through the screen. So, here to use Bond's law, cumulative mass fraction of feed and product are required to calculate the sizes corresponding to 80%. For this purpose, we do the cumulative, and if you see, we have done the cumulative from bottom. This table is basically the initial table where feed and product retained on each screen are given, and in this table we have given the cumulative data. Cumulative we have done from bottom. So, obviously the mesh number of negative screen are shown, as we have shown the cumulative from bottom, we are showing the screen with negative signs over here, and the concept behind this, I guess you understand that we have already discussed. So, this is the cumulative mass fraction for feed as well as product. Now, what is the problem with this data? That here we are given the mesh number, however, corresponding to 80% we have to know the aperture size. So, corresponding to these mesh number for Taylor screen, we should know the aperture of screens. So, if you see in this table, the mesh number of Taylor screens are given and corresponding value of screen size are also given. So, from where I can note down these value? For this purpose, I have to refer the sieve chart, which is the standard chart. This is the sieve mesh chart, where corresponding to Taylor screen, the opening are already given. So, if I consider Taylor screen of 3.5 mesh, I can simply note down aperture as 5.66 mm, and corresponding to other values also we can note down the aperture size. Once I know the aperture size, then these value would be noted down over here. Now, I can calculate the power consumption using Bond's law. Further, to calculate the DFB value as well as DP value, I have to see where 80% will lie. So, if I consider feed, 80% will lie over here, and for product 80% will lie over here. Corresponding to 80%, we can calculate the screen size by interpolation for feed as well as for product. Once I do this, we can have the value as DFB equal to 3.5582 and DPB equal to 1.0121. Work index we have already noted down. So, energy consumption per unit mass is calculated as 1.9904 kilowatt hour per ton. Total feed, if you remember, that is 120 ton per day. So, obviously 120 divided by 24 we will use over here. So, total energy consumption is 9.952 kilowatt. In this problem, total energy consumption has come, theoretical energy efficiency is given to us, which is defined as energy required to create new surface divided by energy supplied minus that required for running empty mill. So, expression goes as 0.3 equal to 9.952, that is energy required to create the new surface, divided by 50, that is total energy consumption, minus EM, that is energy consumption to run the machine empty. So, from here we can calculate value of EM, which comes out as 16.83 kilowatt. So, that is all for example 5. So, summary of this lecture is shown over here, where total 5 examples are considered to illustrate the computation of energy consumption in comminution. So, if you have seen this lecture, this lecture was having two part. In first part we have considered two example, in second part we have solved three different example. Along with this, the computation of energy consumption using Kick's, Rittinger's and Bond's law is shown in this lecture, and the worked example on open as well as closed circuit of crushing are included. So, here we have discussed 5 different example using different comminution laws as well as different mode of operations. So, that is all for now. Thank you.